Okay, we're starting chapter 27. We've actually had a bit. If you were at the lab on Wednesday, you had a part of this. So this is going to be partly reviewed for some of you. Um, we're going to start with the uh, electromotive force. We're just going to call it EMF. It's basically the battery. We're going to talk about direct current circuits now. Direct current. There's two types of currents that we deal with: direct current and alternating current. Direct current is current going just in one direction, and it comes from a battery power supply. Alternating current, otherwise known as AC, is it goes in one direction and reverses and goes in the other direction at a particular rate in cycles per second or hertz. We'll get to that later, but let's just get to uh, the start of it. So the electromotive force is actually it's kind of a misnomer. We're just going to call it EMF. It's the voltage source that you have. So if you hook up a voltage source in series with a resistor, you flip the switch, you get a current. Now, conventionally, we show the current coming out of the positive battery terminal, but what is really happening is electrons are coming out of the negative battery terminal. But we look at the conventional current going in the opposite direction, out of the positive into the negative. So the battery provides the you can call it a charge pump that to push the charges through the resistor back to the other terminal. Now, every battery or a power supply has an internal resistance. So you can see the dashed line. Now I'm not going to spend a lot of time with this. We don't really. There's a few problems. It's we don't really use it that much unless you're working with very, very fine, very, very low voltage, very, very small current devices. It really doesn't come into play. If you're an electrical engineering student, you'll return to this topic, I'm sure, at the time that it's needed. But so you have the EMF, that's the script E, and there is an internal resistance. So the voltage is equal to the E minus IR, which is the current times the little internal resistance. So the voltage you get is the electromotive force, the EMF, minus the IR of the internal resistance. That's what's supplied to the other resistor. So the total E is I times R, which is the current through the big resistor, the circuit resistor, plus the current times the small resistor. And so the current is equal to the EMF divided by the total resistance. Some of you may have seen a small drop. You know, your power supply may have said 10 volts, but you're only reading 9.9 volts when you were reading the current through the resistor. That may have happened. And so the I times E, that's the power. It's equal to I squared times the big R plus I squared times the little r, the internal resistance. And you can see this is a plot of how the potential changes as it goes through the circuit. You know, on one side of the battery, it's zero. It goes up on the positive side of the battery to E. Then it drops a little because of the small r, and then it drops even more all the way back to zero from the big R, and then it returns to the negative side of the battery. So that's just something to be aware of. I'm not going to stress this a lot. Let's just do a small quiz to maximize the percentage of the power from the EMF of a battery that is delivered to a device external to the battery. What should the internal resistance of the battery be? Well, that's probably pretty intuitive. It should be as low as possible. It should be as high as possible. The percentage does not depend on the internal distance, internal resistance. And the fact is, it does, but you want the most of the power to be dissipated in the circuit resistor, not the internal resistor, so it should be as low as possible. There's your answer, as low as possible. Next, we're going to go on, look at series resistors in series and the equivalent resistance. So we're going to be studying series and parallel resistors. This should be a review after last Wednesday's lab.